Okay, in this lesson, we're going to talk about implicit differentiation. And the idea is that we've been doing differentiation in these several forms. Okay, these are called explicit forms because we can isolate one variable. And that might not always be the case. Okay? Lots of our equations are written implicitly, where none of the variables are isolated. And it can be difficult to solve for one of those variables. Here are two of them right here. So you can see that we couldn't isolate y because there's no way we could take it out. I guess we could take inverse cosine. It would be a mess to take the derivative of that. Here, even more so a mess. We want to save time, we want to be efficient, so we use a process called implicit differentiation to find the derivatives of functions that are not solved explicitly. Okay? So it still allows us to solve for dy dx, and that's the best part. We can still find the derivative. It just might involve x and y in this case. So the first way that we've been doing is to isolate y. So in this case, the first thing I could do is say y equals 5 over x, or y equals 5x to the negative 1. Okay? To take the derivative then, dy dx would be negative 5x to the negative 2, or negative 5 over x squared. Okay, and that's our derivative. If we wanted to do implicit differentiation, what we could do is take the derivative immediately without solving. Okay? That would require a product rule because x is being multiplied times y. So I'm trying to do that. I want to make sure that you're thinking about taking the derivative of x with respect to x. So I'm going to take the derivative of x with respect to x and call that dx dx times y plus x dy dx. And the derivative of a constant, 5, okay, is going to be 0. From there I can simplify a little bit. Dx over dx is just going to be 1. So I have y equals x plus dy over dx equals 0. And now I can solve, oops, excuse me, it's supposed to be a plus sign right there. Okay, plus right there. All right, and then I can solve for dy dx. All right, so the first thing I'm going to do is subtract y, x dy dx. Subtract y, and then divide by x. So dy dx equals negative y over x. Okay, well that doesn't exactly look like our original problem, but okay, if I take this and I plug it in here, let's give myself a little more room. Okay, I'll get that dy dx equals negative, what am I looking for? 5 over x, which is negative 5 over x squared, which is what we got when we were doing it the explicit way. So you get the same derivative. However, with equations like this, there's definitely not a way that you could solve for y in which we could take the derivative easily. So here we have kind of a 3-step process to finding the derivative of equations like this, equations that are written implicitly. So the first thing you want to do is differentiate both sides, not just one, with respect to x. A lot of time this will use the chain rule. Okay. Second, you want to collect all the terms with, we're going to be better about this notation, dy dx. You want it to be on one side of the equation, and then finally solve for dy dx. And the reason I'm being a little bit picky about dy dx is when we get to something like related rates. Okay, so just a preview. Related rates, we're going to differentiate with respect to many variables. And so we really want to be careful about saying dy dx, because remember that means the derivative of y with respect to, my abbreviation with respect to, with respect to x. Okay. So let's go ahead and take the derivative of this function that we see up here at the top. Right? I'm going to rewrite it down here just for clarity. My function is x squared plus 3xy minus 2y squared equals negative 4. Alright, so the first step is to take the derivative of both sides. So this will be 2x, and then if I take the derivative of x, think of the x as the inside, that will be dx derivative of x with respect to x. This will require a product rule, so I'm going to do 3, and then take the derivative of x with respect to x, leave y alone, plus 3x derivative of y with respect to x. Okay? Also a chain rule here, so I'll get minus 4y, but then I have to take the derivative of y with respect to x. And on the other side, the derivative of a constant is 0. So that's me doing step number 1. Step number 2, I want to do a little algebra simplification. So anytime I see dx, that's just 1. So I'm going to have 2x plus 3y plus, well, dy dx is not 1, because there's a different top and a different bottom. So plus 3x dy dx minus 4y dy dx, still equal to 0. Okay, so I simplified. Now I want to isolate these terms so I can factor out that dy dx. So if I do that, my left side will be dy dx factored out of 3x minus 4y. And then I'm going to subtract this term and this term over to the other side. So minus 2x minus 3y. All right. And finally, I just want to divide, because I'm trying to isolate dy dx here. I want to divide by 3x minus 4y. So dy dx will be equal to negative 2x minus 3y divided by 3x minus 4y. And that is our final answer. If I asked you to plug in a point, you could plug in the point x and y here. In this next example, we also have an implicit equation. I could solve this for y, but we're going to try implicit differentiation just to get some more practice. And remember, this is an equation of a circle with a radius of 5. Okay? So first, I want to find dy dx. Then I want to find the equation of both the tangent line and the normal line at 3, 4. Okay? So let's take this one step at a time. First, here's my equation, x squared plus y squared equals 25. And I need to differentiate both sides. So I'm going to have 2x and then the derivative of x with respect to x plus 2y, derivative of y with respect to x, continuing my kind of chain rule here, equals 0. Derivative constant is 0. I simplify a little bit with algebra. I've got 2x plus 2y dy dx equals 0. I can divide everything by 2, so I get x plus y dy dx equals 0. And then if I subtract the x and divide by y, dy dx will be equal to negative x divided by y. So that's the equation for our derivative. Now, if I want the derivative at the point 3, 4, I'm going to use proper notation here and say dy dx at the point, or when we have x equals 3 and y equals 4. And then I just plug it in. So negative 3 over 4. Great. A reminder that to write the equation of a line, we want to really focus on using point slope. So y minus y1 equals m times x minus x1. And that really helps us because we don't have to solve specifically for the y-intercept. So I've got my point, 3, 4. I've got my slope here. So my tangent line equation at 3, 4 will be y minus 4 equals negative 3 fourths times x minus 3. If I want an equation of a normal line, though, a reminder vocabulary that normal means perpendicular. Okay, perpendicular. And if something is perpendicular, that means the lines have opposite, reciprocal slopes. Okay, so that means if I want the equation of the normal line at 3, 4, I use the same point, y minus 4 equals slope times x minus 3, but I take the opposite, make it positive, reciprocal slope of the tangent line. And there it is. That is the equation of my normal line at 3, 4. Okay, so one thing that we haven't really covered yet, but I think intuitively might make sense, is the second derivative. And the second derivative is just the derivative of the first derivative. So you would be taking two derivatives from the original function. Okay? To do that, you first have to find the first derivative. So if I wanted to find the second derivative, which is what I'm going to get to in part B down here, of this circular function, okay, again, this is a circle of radius 3, okay, I first want to find the first derivative. Well, I'll give you a hint. We already did this in the last one. It's going to be the same for all circles, and you can prove it to yourself if you would like. Okay, make sure you take the derivative implicitly, but you'll still get negative x over y. Okay, so that's my first derivative. To find my second derivative, I'm just going to take the derivative of this. That will require some quotient rule, though. And the notation for second derivative means taking the derivative a second time of the function y with respect to x both times. Okay? If I use my quotient rule, I'm going to use low d high. Okay? And again, you can write dx if that makes you more comfortable. I'm going to skip that step this time. Minus high d low. Well, dy dx is not 1, so you know I got to write that. All over low squared. Okay? Now, if we had numbers that we could plug in here, we could definitely evaluate dy dx for a number and then plug it back in. But since we're just looking to solve for an equation in general, I need to take my dy dx and plug it in. Okay? So, if I plug that in, I will get negative y plus x times negative x over y squared. On a free response problem, don't forget, you can just leave it that way. But just because we like things a little more cleanly, let's simplify it a little bit. Okay, so I want to get a common denominator here. So I'll get negative y squared minus x squared over y times y squared, which is y cubed. And that can be my final answer. Okay? Alright, so let's try that again with another function. And this time we will choose not to simplify. So my function is y cubed equals 4 minus natural log of x. So first I find my first derivative. Oops, excuse me, but I'm taking it implicitly, so I need to make sure I pay attention. So 3y squared dy dx. Again, just in case you've forgotten already, this is us using our chain rule. We took the derivative using the power rule first and left the inside the same, and then took the derivative of the inside, and that's how we got dy dx. Equals, well, derivative of 4 is 0, and the derivative of natural logs minus 1 over x. Okay, and I want to solve for dy dx before I start taking a second derivative. So I am going to get that dy over dx equals negative 1 over 3xy squared. And that is my first derivative. All right, then I'm going to move over, take my second derivative. So d squared y over dx squared will be low d high. Well, take a look. The derivative of high is just going to be 0. So that first term is going to be 0. Minus high d low. We got to do product rule. So 3y squared plus 3x times 2y dy dx. All over 3xy squared. And I told you we weren't going to simplify it, but we do still have to plug in that first derivative. So our final answer is going to be 3y squared plus 6xy, I'll simplify that a little bit, times negative 1 over 3xy squared over, oh, I forgot about squared here earlier, 3xy squared squared. So the last page here, little conclusion, right? So in problems where you need to find the second derivative with respect to x both times of an implicit function at a point, okay, so at a specific point, a given number on the curve, you can simplify your algebra by first finding the value of dy dx at that point, and then once you take the derivative, all you have to plug in is a number instead of an equation. So let's see how that might work. Oops, too far. Okay. So this, they've given us f is differential for other numbers. The point 3, 1/4 is on the graph of f, and the slope at each point is given by the, wow, they already took the first derivative for us. Okay? So to get to the second derivative, all I have to do is take the derivative of dy dx. So let's write that out. Dy dx equals y squared times 6 minus 2x. And you could distribute the y squared if you would like, but regardless, you're still going to have to do a product rule, so we'll just do it this way. So the derivative twice of y with respect to x both times is 2y dy dx times 6 minus 2x plus y squared times negative 2. Okay, and here's where you would be like, oh, I don't want to plug this whole thing in right there. Okay, but I can evaluate this to start at 3, 1/4. So if I do dy dx at 3, 1/4, I'll get 1/4 squared times 6 minus 2 times 3. Well, awesome. That's going to be 0. And when I plug that in, now, down here, so I'm taking the second derivative at 3, 1/4, I'll get 2 times 1/4 times 0, 6 minus 2 times 3, that's also 0. But then plus 1/4 squared times negative 2. Okay? And when I multiply, my final answer is over here, I should get negative 1/8. And that is my second derivative. Okay? So it was much easier than having to put this equation in here first and then having to do some algebra. It's nice if we know what that is, that the first derivative is at that point, to just plug that in. Okay? Second question though, a reminder, find the equation of the tangent line to the graph. This will show up a lot. Tangent line to the graph at that point. Well, the tangent line, I need a point, which I have, and I need the slope at that point, which I also have up here. That slope is 0. So if I'm going to write my equation in point slope, I'm going to have y minus 1/4 equals, slope is 0, times x minus 3. So if I simplify, I'll really just get y equals 1/4, okay, a horizontal tangent line.